acceleration of the stuff attached to the rope is equal to the translational acceleration at this point. That's a huge concept. You'll use it all the time in problem solving. Write it down. And you can see it if you look at the picture for the problem in the upper left-hand corner. I've been doing this for a long time.
All right, bye, Mr. Lindsay. I love you.
See you, Dean. It's
I
cool
love
to call you that, right?
It is, you're graduating.
Love you.
Yo, some way, somehow, I got your phone number.
Wait, message me on Facebook. You never reply.
You did message me.
I will message you though,
Okay.
and you better reply.
Yeah.
Don't cheat.
The, if you look in the picture, on the upper left-hand corner, you see the package where it says T equals W minus MA. That MA is the A of the package. But you can trace it up the rope to where it touches the pulley. And at that point of contact, that's also the translational acceleration of the wheel at that point. So, if you know the alpha for the wheel, the translational acceleration of these packages is alpha R, or this is R, for the wheel. That's huge. It seems like such an easy concept, but people forget it all the time. And remembering to do that will make all the difference in the world. Okay, so kind of on that note, T2 is bigger because there's more mass on the side. So the system is rotating clockwise. I'm going to make clockwise positive. There's two other forces here I didn't draw. What are they? Weight of the pulley and
the normal force.
the reaction force in the hinge, which we can call a normal force, that's fine. The reaction force in the hinge is canceling out all three of these. Why?
Because the pulley's not being held.
Because the pulley's not accelerating downwards, right? Because the pulley's being held where it is, because sum of forces in the y is 0. Because of that, all these forces are canceling out. Sum of forces can't give us a lot of information here. Let's do sum of torques. Sum of torques equals 0?
No.
What?
Oh, and alpha.
M alpha?
Or I alpha.
I alpha. That's the rotational version of MA. Let's take a second and look at that. If you've got, let's just imagine a system that's spinning with some force on it, okay? So what I've done is I've attached a rocket to a rod and pinned it in place. It's a pretty cool invention. I made it. So the rocket's shooting straight up here. It's fixed on the rod, but only the component of the thrust force of the rocket that is tangent to the rocket's path, only this component of its force is making the rod system accelerate. Does that make sense? This is just kind of pulling on the rod. It's not going to accelerate. If the rocket was pointing straight out, it would just hold there. It wouldn't spin. But because part of it's pointing at an angle, it's going to go in a circle. So only this component of the rocket's thrust force is making the system accelerate. Now, in this case, here's the thrust force of the rocket causing the tangential acceleration based on the mass of the system. I just told you instead of AT, we can call that R alpha. So that means the thrust force is mR alpha. What if I multiply both sides of the equation by R? Then the torque, because of the rocket, is mR squared alpha. What's RF? Radius times force. What is that?
A torque.
That's torque. So that means torque is equal to mR squared alpha. What's mR squared?
I.
That is I for a point mass. That is a point mass as I. And in this case, that point mass is the rocket. The rocket's exerting a force, the rocket has this mass. If I add up all the different torques in my system, that means I'm adding up all the different moments of inertia to get the net alpha, so torque is I alpha. For individual torques, use R cross F. For net torque, use I alpha. Alright, back to our okay. Sum of torques is I alpha. I've got two torques here, right? T1 and T2. Which one's positive? T2. It's making it spin in the direction that I identified as positive. T1's trying to make it spin the opposite direction. So T2 times the radius, which is, remember, the distance the force is acting from the axis of rotation, right? Radius points from axis of rotation to point of application. So T2 times R minus T1 times R is I alpha. Not too hard. Okay, what about this one? MG is pointing down. Yep. What else? Tension's pointing up. What else?
There's a reactive force.
There's no reactive force at the pulley.
Oh, I know that's not.
This is only the forces on the pulley. I have a question. This is a really fun demonstration. I've got this right here, right? Here's the pulley. Here's the rope. I'm going to drop it. When I drop it, is it going to drop straight down? I'm going to hold on with this hand. I'm only dropping with my left hand. Is it going to drop straight down? Is it going to swing to your left? Or is it going to swing to your right? When I let go with this left hand. Talk to the people at your table on the side.
I thought about it, but I don't know why. I'm thinking, see if this is open, then it goes down, and then
Yeah, once you unroll like something like that, it's never
Never the same.
Imagine how hard it must be for
We should start a campaign.
Oh, that's of course, right?
Pay $1 and we'll free robots.
Free the robots.
A robot there. Oh, sigh. That's
Yeah.
not good. You think you know?
Are we supposed to say our answer?
No, you just like, I was just kind of like waiting. I didn't have to say, okay, quiet everybody. You just were like,
We want to know.
okay,
We're
Phil's
eager-
pretty much the
we're
loudest
eager
personality I've
learners.
ever taught. So when he comes in the room, everybody gets quiet.
Who?
The guy who's in here.
Uh,
So, what's it gonna do? All in favor of it's gonna fall straight down. Raise your hand. David.
I heard the question.
Okay, all in favor of it's gonna swing to your left. Raise your hand. And all in favor of it's gonna swing to your right. Raise your hand. Okay. Some people aren't convinced, so get on your soapbox. Convince us why you're right. Let's go. Who thinks they're right?
What's a soapbox?
Get on your soapbox is a phrase for say, stand up and speak loud about what you're passionate about.
It's like a long time ago, people would like put random soapboxes and like stand up and just yell at people and say like, find Jesus or something like that.
Why do you gotta be Jesus? Chris.
I feel like because the center of mass is at the center of the circle, and the center of the circle is to the right of where it's anchored, then the center of mass will naturally pull downward and will move to the left because the where it's anchored. I don't really know how to describe it in terms of science, but that's just what my thoughts are.
Assad.
Like since your hand is like right under it before that, is you moving your hand to the right? I think it's gonna slide to the
I'm super quick. Yeah, don't take my hand into account. Hasid.
I thought it would fall straight down. Since MEG is pulling it directly like down, there's no force acting on it. It just goes straight down. But the tension's not giving it acceleration. So only MEG is, right?
Okay. Alex.
I think like in a perfect physics world, it would go straight down, but since there's friction, it will go to the left. So
What kind of friction?
just between the paper as it unwinds.
There's friction between the papers that unwinds? What kind of friction? Static or kinetic?
Static.
So then it turns into kinetic?
I mean,
Which way is friction pointing?
so like the friction, like you know the bottom of your hand,
Yeah.
like the friction there would point left on the roll and right on the paper. And so I think because the center of
So
mass
when I
is-
let go, there'll be friction pointing this way.
sort of,
Friction always points parallel to a surface.
yeah, so like the bottom of the, so yeah, or maybe it would be pointing like that.
That means circle out.
Because I think cause like sort of what Chris was saying, like, I think the center of mass will like swing down.
Gotcha.
Tension is tangential, so there's no x component of force acting on the pull.
Therefore,
It goes straight down.
other thoughts? Let's test it, shall we? Okay. 3, 2, 1.
Whoa.
What did it do?
Straight down.
Straight down.
That's not really.
No, you didn't. Okay, why did it go straight down?
Because of what Patrick says.
Because what Patrick said. Patrick was right on. There's no x force. There's no force in the x direction. So the center of mass is not going to move in the x direction. Fall straight down. Crazy.
I don't.
That was horrible.
Shoes
Mike.
never lost their squeak.
I can make a squeak.
Wait, how? Like seriously, tell me because I need to know. Because
Give
my
me a-
mom can something up like
Give me a
that.
barrel and some gasoline. Okay.
What are you gonna do?
Okay, this one's a fun one. And on this one, this is a good one to talk about the importance of drawing your forces at the point of application. What am I going to do with that? So what are the 3 forces acting on the wheel with friction? I was just laughing at you. That's what I was going to do with the barrel.
Oh.
I'm just going to wash them.
What are you? Yeah. That's about it.
We got mg. What else is acting? Pointing which way? To the left. Put friction where it's acting. Okay? So I'm going to draw it right there. Static or kinetic?
Kinetic.
Why?
Because it's
moving.
moving.
Because it's moving. I have a question.
Kinetic.
Wait, I think
Oh no, he said I have a question. That means we're wrong.
I have a question for you guys.
Oh, physics questions always make me feel dumb. Alright, watch the wheel. Is the bottom of the wheel moving with respect to the table?
No.
No, it's not.
It's ecstatic.
Like if you were a little person standing in here and the wheel came by, you could just step right on there. Because the wheel's not moving with respect to the table. When a car drives by in the mud or in the snow and you look down to where it drove, what do you see?
Oh,
What is
track.
You see tread tracks.
see
yes.
sound.
You see the tracks where the tires were in the snow. Because you can see the tracks, that's because it's like they're just like pressed down. The point of contact has 0 velocity. A car going down the road at 90 miles an hour has 0 velocity where its tires are making contact with the road. When you're driving home today and you look at the speedometer, just keep in mind your tires are not moving with respect to the road. That's
Wait a
weird.
minute. So
Yeah.
is the top of your tire going at twice this
Yes, it
speed of
is.
your car?
Uh-huh.
No way.
So if you're going 90 miles an hour down the road, the top of your tire is going 180.
Oh,
And I'll explain that later. It's,
So-
it's
so
great
like-
you already said it, but I'll
so-
go into the detail. If you're
So
a
if
little
you're
bit like,
trying to like act cool or whatever, I drove so fast the other day. My tires were going 90, and you're only going like 45 miles an hour. Yeah.
so
I've got
the,
90 before.
where the wheels are in contact with the ground, the speed is 0. This is called the no slip condition. For those of you that have been reading the book, They talk about that. This means no slipping or no sliding. The no slip condition assumes that the speed here is 0. Now, if I am slipping, that means that there is a little bit of kinetic friction. Otherwise, there is a little bit of kinetic friction between the tire and road because it's slipping. Kinetic friction causes a deceleration or an acceleration in the x direction. This is cool. Objects need friction to roll, right? If I tried to make this thing roll and there was no friction, it wouldn't roll. It would just slide. If you set a wheel at the top of a ramp and you let go and there's 0 friction, it just slides down. Yeah.
Like, you know how, like, when you play pool, like, when you hit it, like, really hard, it initially doesn't roll until, like, the friction, like, catches?
Exactly. We will solve problems that figure out how long it takes for that to happen.
The pool stops when
Yeah.
and then, because there's no spin.
Well, yeah, and that's elastic collisions as well,
Yeah.
because they're the same mass.
But then if it has time to start rolling, the top spin will make it keep going.
Exactly. Yes.
So, if it's like 2v at the top and 0 at the bottom, does that mean that angular velocity isn't the same everywhere?
No.
But it's all the same wheels.
I like it when you have trouble with a problem, Andrew, because you're just like, wait, I usually get this class. I'll explain later.
Now you know why.
Oh. Okay. There's one more force. I don't know where my marker went. What's the other force?
Normal force.
Normal force. Found it. All right. So, if you want to sum torques, where's your axis of rotation here?
The center of
In the center of the seal. Center of the wheel. Duh. Right there. What is the torque due to normal force?
0.
0. Normal force is pointing parallel to the radial arm. Normal force is causing no torque. Normal force doesn't make it slide. What is the torque due to mg?
Well, we need a theta.
0. Because mg is pulling from the center. Right? I can't push on the center of this wheel and make it spin. I have to push some distance from the center. What's the torque due to friction? Is friction causing a torque? Yeah, it's spin clockwise. So the sum of torques equals I alpha. In this case, it's the force of static friction times the radius equals I alpha. Okay. When a wheel is rolling down a ramp and not slipping, something cool happens. You can't usually do this. Normally when objects are rotating, there's only one axis of rotation. You have to pick the axis of rotation that is 0 velocity. In this case, there's another axis of rotation you could solve this problem from. There's another place we could choose to be our axis of rotation and get the same answers. Still solve it.
Wherever the balls can contact the ramp at that point? Is that right?
Yeah. If you choose this as your axis of rotation, how much torque is friction causing? None. 0. How much torque is normal force causing? None. Friction and normal force are pushing on the axis. They can't cause any torque. How much torque is mg causing? Well, how about this? Is all of mg causing a torque? No. Right? Only the part of mg that is perpendicular to the moment arm. So, this is my axis of rotation, and here is the moment arm, it's mg. If you want, that's one way to look at it. You can look at it like that and say, I'm going to use all of mg and move mg to here. All right, that was our flexibility, being able to move the sine theta that we learned yesterday with that ladder problem, right? I can say it's mg times the radial arm sine theta. This is the radial arm.
Oh.
I still don't like that.
That's fine, you don't have to like it. Right? That's r sine theta times mg. Or you can say, I want to take mg sine theta, which is this vector right here, times r. You can do mg sine theta times r, which makes it spin this way, right? That's going to cause it to spin that way. Or you can do r and g sine theta, which is also going to make it spin that way. Pretty crazy, huh? Any questions on that?
So in this case, mg doesn't have to always be the hypotenuse.
Where is mg not the hypotenuse?
First thing
Nope, mg is still a hypotenuse. We were using all of mg. I didn't break it up into components. When I did this, I said I was just going to take this little component, this sine theta of the radius, and multiply it by mg.
So mg is applying to it?
If you take the perspective that this little dot, oops, dot didn't come with me, little dot is your axis of rotation. Other questions? Pretty wild, huh? I think it's cool. I think it's very cool. There's no friction. What are my forces?
Just
mg normal force.
Just mg normal force. Is it rolling?
Nope.
No, not rolling. Notice how I drew normal force from the point of application. You should always draw your forces from the point of application of this unit. Alright, this is a cool one. David, what are my forces?
There is mg in the center of the ladder.
There is mg in the center of the ladder.
There is a normal force from the bottom of the ladder that's touching the floor, and at the top of the ladder going perpendicular from the wall. There's also a force of friction pushing.
That doesn't say there's friction, so assume there's no friction.
Okay.
Hey, are those two normal forces the same?
No, they're not.
No, they're not. What is the path of the center of mass of this system?
Slightly to the right.
Straight down.
Yeah.
No, that's
Down and to the right.
Down and to the right. It's going down and to the right.
Because there's two external forces.
And now I'd have to think for a minute or two to figure out if Fn2 is changing linearly or exponentially, but it is going to move down and to the right. That's the path of the center of mass. Because there's a net force pulling it down, Fn1 minus mg, and there's a net force pushing it to the right, Fn2. This is a fun one.
Wait, so then eventually, once that hit the ground, would it just keep sliding to the right forever?
Yeah.
At a constant velocity? Right?
Yep, at whatever velocity the center of mass has in the x direction when it hits, it'll keep that velocity. Because even the hitting on the ground exerts a vertical impulse on it.
Yeah.
So it doesn't, so since there's no friction, there's no horizontal impulse. Pretty cool, huh?
Yeah.
It's a good test question.
Uh,
Okay, what about this one? I probably won't ask that in the test, for those of you that are always trying to figure out what I'm asking in the tests. MG, what else? Anything else?
Hinge force.
Force, the vertical force in the hinge.
There's a hinge force pointing up or down. Everyone sure?
Yep.
Why is it pointing up, Serena?
Because.
Serena?
Oh.
Miss Patel? Yeah?
I heard some.
It's rotating that way, good. Why does that mean that it's going to have to point?
That's the opposite. Knees push it the other way.
Yeah, it's kind of like this. If that wasn't there, what would it do? If the hinge was not there, what would the beam do? Just fall straight down, right? So the beam's holding up, or the hinge is holding up this end of the beam. The hinge is saying, no, you stay here. It's like anti-accelerating it. It's holding it in place. I like this one. Let's see. Paul, what are the forces on this? There's mg. Always draw it at the center of mass. What else?
There must be a normal force.
There's definitely a normal force, which is not as big as mg. What else? Everybody agree? You know what force? Well, the normal forces come from the hinge.
No.
Oh, give someone else a chance. Give someone else a chance.
Is it because the hinge is at the axis of rotation, so that's why the force there would be zero because there's no distance?
Oh, you're talking about torque though when you say that, so, no, that's, no, not really. David?
Whenever you have like an hinge force going, like a parallel hinge force going into the platform,
Like that?
that,
Like that?
yeah.
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 Why?
Because if there weren't a force like that, then the, the Y component of mg would make the platform come through that thing.
You're right, and there's an easy way to think about it. What's the path of the center of mass?
Down to right.
Yeah, looks like this.
Semicircle.
Or quarter circle.
From
That's the
pi
path
over
of the
2
center
to
of
0.
mass. So what? From pi over 2 to 0, yeah. So, because of that, the center of mass is accelerating down, and it's accelerating to the right. And David, you were correct. It's just that we didn't draw the force like that. We drew the two components of that force. See? So we didn't need to draw the one that's up in the beam. We drew the two components. You wouldn't draw both. We're just drawing the components of hinges.
So you. Wait. But you were not supposed to draw both?
This and this, yes. This and this, no. I said don't draw this vertical thing and draw the one that's up in the beam, right? Because it's redundant.
Okay.
Drawing these two components is exactly what you should do.
Alright.
Alright, the floor is frictionless. How does the center of mass move?
It goes clockwise, straight down.
Straight down.
Straight down. There's no forces in the x direction. The center of mass only moves when there's a force on it. Do you feel like you're finally starting to get some of these topics? No, even from the other, like, I mean, we're talking center of mass a lot right now, and all this center of mass discussion is stuff from the last test, and so I hope that maybe, like, the fact that this class is cumulative means you start to catch on.
Oh,
If nothing else, it's osmosis.
that stuff,
What? Yeah.
So for RN6, I was thinking about it, would the path of the center of mass be a quarter circle? Because
Which one's number 6?
it's the one where it's up against the wall and it's falling down like that. Because I feel like,
Yeah, and I think it's a quarter circle that's like this.
yeah, because like as it's falling, then this is like cosine sine of the triangle, and so as it falls like that.
Yeah, I think so. You're right, because it's just going to follow a path of the triangle.
Yes.
Cool. That's a neat observation. I just figured out some neat math you can do with that. Infinite triangles out here to get circle, infinite right triangles, so that the circle would fit inside of the square. You see that?
Oh, yeah.
Okay, we're done. Cool. Let's see, I think the next thing I want us to do is we'll look at this problem. So, the engine of a small airplane is specific to have a torque of 60 Newton meters. This engine drives a 2 meter long, 40 kilograms propeller. On startup, how long does it take the propeller to reach 200 RPM? This is an easy question. Oh, it's written on the board. Ah! Isn't it kind of redundant that I'm erasing it just to write it again?
Yeah, you can just stand in front of it and do this until you all know.
When I write, you'll learn it better. And when I write, there's a chance you'll write too. Okay, so I'm trying to find the time it took to get somewhere. Let's write down our givens. I know that the initial speed is 0. The final speed is 200 RPM. Get out your calculators, tell me. What is 200 RPM in radians per second? Go, 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 calculators.
radians per second.
20.9.
Multiplied by 2.1.
Okay, what do you get for radians per second? 20, I think it's
20,
20.9.
20.94.
That's what I got. 20.9. Okay, I know, you know what, I bet if I could find alpha, I could find time. And alpha seems like a number that's reasonable to find. So let's develop some equations to find alpha. I know the torque, and I know the torque is pi alpha. I know I is 1/12 mL squared. I can find alpha now. 60 equals 1/12 times 40 times 2 squared. What do you get for alpha?
Alpha's 4.
4.5?
No, it's just like 4.00000.
I think it's 4.5.
Exactly.
Mr. Landers,
What's up?
it's me.
Okay, see ya. Work on those AP bubbles.
Yes, sir.
Okay, plug that into the original equation. I'll get out of your way in a second. Oh yeah, turn that other book. Yeah. Oh my god. Okay, hopefully you got 4.6 seconds for the time. The solution's on the notes online if you want to go check it out later. Okay, typically, you do not use torque. Torque is not usually a number that's, torque is a number in and of itself, right? We're not usually saying like, torque is 2 Newton meters, so find something else, right? Normally, you're given a system with a bunch of forces acting at some distance that has some moment of inertia, and you're using alpha somehow, right? You usually use these equations as you see in the yellow box.
Whoever has this. Good. Like the formulas work with it.
We sum an infinite number of torques.
Like infinite number of stuff.
I mean, thinking. Yeah, I can think of a case where you might have to do that. Not for this class. Let's look at some stability questions. So you're driving like a maniac and you rock up on your 2 wheels in the SUV. Are you going to roll the car?
Well, it depends on the center of mass.
Omega is 0 in this picture. And the center of mass is marked in the picture. Are you going to rock the car?
You're gonna rock it and roll it.
Rolling.
No.
Well, rocking, not rolling.
You have to roll.
Okay. Is torque positive or negative in the picture?
Negative.
Why?
Because
It's going to rock back down clockwise, right? If it's at rest here in the picture, it's going to rock back down. We got a negative torque. Look at this one. Whoa. Now you're really driving crazy. Okay. At this point, what's the torque?
0.
0. The torque is 0 in this picture. So,
Yes,
that's
that way.
Can you explain the one before that? Because if you're going that way, wouldn't that be positive? I mean, I understand you're gonna rock back down, but are we talking about torque when it?
right now, omega is 0. Angular velocity 0 in direction.
Okay, and because you're not gonna completely roll.
Yeah.
Okay, I got you.
Omega 0 here.
That happens in the movies.
Yeah, not in real life though. And because here, obviously, right, we're dealing with things that are too subtle. Like it just takes a little bit to knock it off because the center of mass
Oh my
has to
gosh.
fit within this footprint. Right, and so a little bit to the left, a little bit to the right, boom, you're done. Mr. Ketchup Face, what's up?
If that situation were to happen in like real life, which way would you have to turn the wheel in order to get that home? Well, turning the wheel help, right?
I would turn my wheel to the right.
Yeah, to the right, so you can catch it.
But I mean, it depends. There's too much. You
Just
you
jump
bail.
so fast and do
You
something.
bail.
Planning on getting in this
Internal
situation?
forces. Internal forces.
Yeah, but that works in real life.
But if you bail, then the car will rock.
Okay,
Wait, hold on, can you
it would because of friction on the ground. Okay, what about this one?
he's not
Car falls.
Now you're rolling and rocking. Right, you're gonna keep on going, and it's toward positive or negative? Positive, because we're gonna rotate counterclockwise. Okay, we'll save this problem for Monday. I want you to get out those 2 AP problems.
What?
You pick up 2 AP problems at the door.
Okay, no one ever tells me these things.
Well, you just gotta know where. You're working on those till the end of class.
Yeah,
Team.
yeah, I mean, this is.
Patrick, turn off the projector.
Oh, Patrick.